Okay, yeah, my talk today is about endoscopy for Affine Hecke categories. A paper of same name has been uploaded on the archive. Yeah, the code is, the number is here. So here is my table of content. First, I will talk about Hecke algebra and their generalizations. And then I will move one categorical level up. It's about Hecke category instead of algebra. I will mention certain properties of Hecke category, and then I will move on to talk about endoscopic group, which plays a huge role in my paper. And then I will state my main result of the paper, which is, roughly speaking, about monoidal equivalence between two derived categories. And then I will sketch a proof. So here is the notation. My G is a split reductive group over FQ. For instance, you may think about GLN, the n by n matrix, invertible matrices, symplectic group, and also EH, the most complicated exceptional group. And my B is a Borel subgroup. In the case of GLN, it just consists of upper triangular matrices. And T is a Cartan subgroup of B. Again, in GLN case, you can take the diagonal matrices. And W is denoted as the Wau group, which is symmetric group for GLN. And LG stands for the loop group. Its FQ point is just G, the Lorentz series polynomial point of G. So in GLN case, it's just n by n matrix, but the entries are the Lorentz series. Finally, my W tilde is the alpha Wau group. It is the semi-direct product of the finite Wau group W and with the co-character letters. So So now I could talk about what Hecke algebra is, which I denote as HQGB. So first of all, as a vector space, it consists of functions on GFQ, the FQ point of G, with by invariancy condition. Namely, if you left or right multiply an element in BFQ, the function doesn't change. In other words, you may think of it as function space on this double coset with QL bar value. The QL bar here, is just for geometric purposes. You can replace it by C, the complex number. But they're abstractly isomorphic. And I could give these functions an algebra structure by using the convolution formula. And notice that the functions on GFQ is an algebra by this formula, the convolution product. And it is easy to check that if F1 and F2, these two functions are bi-invariant, then the resulting function is also bi-invariant. In other words, the algebra structure descends to this subspace. We could use a diagram to describe this formula. So suppose I have F1 and F2 here. It's a functions on G mod B mod B. Oh, here my G and B are finite group. I just So first, I could pull back these two functions along these two projection map and take their product. And this B is acting on G cross G by diagonally or anti-diagonally. So then I could push forward along this map. So in other words, push forward in functions language means integration along fiber. And then I will get a resulting functions F1 star with F2. So pull back, take tensor product, and then integrating along the fiber. I should mention that, okay, this Hecke algebra has dimension W, the cardinality of wild group. Yeah.
Excuse me, just an ignorant question. When you say dimension, you're thinking of these as algebraic groups or varieties, or exactly, I'm a little confused by your notation, G upper cross upper BG. Is that an incidence variety, or what exactly is that?
It's okay. First of all, everything it's not variety, it's just set.
Okay, all right.
So the dimension here is the functions on double coset.
I see. The functions.
And then this double coset is indexed by W by Buchert decomposition.
Okay.
So yeah, and then G cross B G, yeah. So the action is G B B inverse G prime.
Okay.
So yeah. So you could somehow collapse this B action. Yeah. And yeah, if you think K as a variable, you may think of it as this Hecke algebra is some kind of deformation of the group algebra of wild group. If you take Q equals to 1. So, okay. So why do we study Hecke algebra? Again, G and B are finite group by Abel's notation here. If I have G add on V, so B will add on V by restriction. If I further assume the B invariant subspace is non-empty, then the Hecke algebra actually adds on the invariance of space. In this case, the B invariance of space is usually much smaller than V, so it is easier to study. And also, another reason for studying Hecke algebra is it is the endomorphism ring of the principal series. Namely, yeah, if you induce from the finite group BFQ the trivial representation to the whole group GFQ, then you study endomorphism of G induction from of the trivial representation, then you will get this algebra. And it plays a role in classification of finitely group, the representation of finitely group. So I can move on to the Affine Hecke algebra. So basically, I replace everything by its affine analog. Namely, well, GFQ will become loop group, so LG, or in other words, GFQ bracket T, double bracket T. And now the Borel will become Iwahori in this affine language. The Iwahori is defined by this fiber diagram. So basically, if G is GLN, then it just sum n by n matrices. If you plug in T equals to 0, it becomes upper triangular matrix. So it's not very like this. And then, okay, you could similarly consider the functions of GK with by invariance condition.
Script on the Iwahori there in that diagram.
You mean this one?
Yes, what is that? Sorry.
Oh, it's fiber diagram. It's fiber product.
I see.
Yeah. To the two, I don't know, 90 degrees perpendicular thing. Yeah. So I only consider compactly supports because this time the dimension or the double coset is indexed by alpha and 1 group. So I don't want to consider the infinite support. So yeah, basically it's just some algebra. Well, on the other hand, I could generalize the Hecke algebra to something more general, namely the monodromic Hecke algebra or monodromic Hecke module. So this time, I consider G mod U mod U. So U is the upper unipotent radical of B. So in GLN case, it's just strictly upper triangular matrix. And then, okay, now I put two conditions on these functions, namely, if I left or right multiply by an element in UFQ, you still get the same value. And also, if I first fix two characters of finite group, this is a finite group. So yeah, and then I require that if you left or right multiply by an element in TFQ, the finite torus, it change accordingly to the character value of T1 and T2. So yeah, is a special case when chi1 and chi2 equals to trivial character, then we just obtain back to the Hecke algebra I mentioned before. So basically, I changed this monodromy. Similar to the finite Hecke algebra, I could use some diagram to describe this the algebraic structure or the product structure. Suppose I have a functions f1. No, I have two functions f1, f2 on this Hecke module or Hecke monodromic Hecke algebra. This space of function. Notice that I require these two. The right monodromy of the first one coincides with the first monodromy of the second functions. They are both chi2. Then I could pull back with these two net canonical projections. Since these two are chi2, I could actually descend the functions on this B quotient instead of U quotient. In other words, the T orbit, the values on this, the middle T orbits are the same. So I could descend the functions. And then I push forward. So integration along the fiber. I get this F1 cross F2. You can check that the monodromy will be preserved. So in other words, if you consider chi1, chi2, chi3 are the same, this formula will give you an algebraic structure. And if you only require chi1 and chi2 are the same but not chi3, then you could see that H chi3 chi2 H chi2 chi3 is a module over H chi2 chi2. So that's why they are called Hecke algebra or Hecke module monodromic. So yeah. Well, there is another description for this product structure. Namely, if this is the point I'm going to talk, so you the monodromic Hecke algebra or module can be reinterpreted as a homomorphism space of G, FQ, and this is all finite group. These two representation home space. So the product structure I mentioned above precisely corresponding to the composition of the homomorphism. And notice that not every double coset could support the functions. Yeah, because there are left monodromy and right monodromy. You could see if G equals to E, yeah, somehow they have to have some compatibility. If you expand this compatibility, you will find that, okay, this is precisely the subset of the double coset that can support the functions. Similar to the Hecke algebra, the H-chi-chi will add on some twisted invariance subspace if G adds on V. Now we could combine two generalizations together and obtain the Affine Hecke monodromic Affine Hecke algebra. So I replace unipotent radical by IU, the unipotent radical, the pro-unipotent radical of Iwahori. So this is, yeah, I don't know. This is also evaluation at T0. And I also require that it has some monodromy. Then I also consider the compactly support function. So yeah, if chi1 and chi2 are the same, then it is an algebra. Otherwise, it is a module. So far, any questions? So basically, I define a monodromic Affine Hecke algebra. And the algebraic structures are given by convolutions.
So what do you mean by VU chi that you wrote on the above? The monodromic affine Hecke algebra acts on, yeah, that.
This one.
Yeah.
Oh, so basically I want to say you consider the U invariance of space and then T still adds on it. And then it will decompose according to the character. Maybe I use mu. So I take the U invariance of space and then the torus still add on it, and then it decomposes into eigenspace. And then I take this particular eigenspace. And then you could check this H-chi-chi act on VU chi. Any other questions?
So that's a particular graded piece, right?
Yes, if chi equals to trivial, then yeah, and then this just reduced to the B invariance.
Yeah, okay.
Because you just take U invariant and then take torus invariant, combine together, it becomes B invariant.
Mm.
Well, the coordinate philosophy tells us, okay, sheaves are better than functions. So if I have a sheaves, and then I could, on a variety, I could take the trace of Frobenius, and then I will obtain a functions on FQ points of that variety. So now we should consider one categorical level up. So it's Hecke category instead of Hecke algebra. So yeah, they are the derived categories of constructible sheaves with respect to Boole decomposition. So this is the finite case, finite Hecke category. This is the Affine Hecke category. Yeah, I wouldn't be able to explain the definitions of these derived categories. If you're interested, you could read the famous book by Beilinson, Fang-Ting, Deling, and Gerber about perverse sheaves. Instead of talking about the definitions, let me mention properties that we actually how we work on these two derived categories. And these properties are also, yeah, you could see the reference in this book. First of all, they are triangulated with a particular T structure. And the heart of this T structure is the equivariant perverse sheaves. And secondly, if you have an element in the Wau group or affine Wau group, there exists 3 perverse sheaves associated to this element. They are called standard, IC, and co-standard, which are denoted as J streak, star, J star. So yeah, the J streak and J star, I suppose you're familiar with because they're more everywhere in algebraic geometry. J streak is just extension by 0. And the middle one is the most interesting one, the IC sheaf. They are the simple perverse sheaves. So basically the Poincare duality holds for this IC sheaf, and that makes it so special. So there are 3 types of perverse sheaves I'll consider, and these 2 derived categories are monoidal categories. The formula are given by as before, as above. Just as the function case, you pull back the sheaf, take tensor product, you push forward. And the 4th property is so-called T-twist. Here I would, so whenever you have a sheaf, you could twist with 1/2, for example. So in other words, it's just like some grading of the derived categories are graded. So you could move upwards and downwards. But this grading is not the same as the cohomological grading. So usually when you think about derived category, it's like some chain complex. You want to move shift to left or right. But yeah, this T-twist is more like the object-wise in the chain can move up and down. And the 5th property is whenever you have a open-closed triangles. So open embedding from U to X, and then the complement, I call it Z, you get some triangles. This is a distinguished triangles. Let me give an example. If G is SL2 and X is the flat variety of P1, then X is naturally stratified into 2 pieces, the 0 point and the complement of 0. And then if you expand this distinguished triangle, you will get these 3 terms. And notice that since they are all perverse, so the end has to be 0. So it is a short exact sequence. So the punchline here is that the standard sheaves can be somehow reconstructed by IC sheaves, which I will use these properties in my proof. And the sixth property is for any two sheaves, F and G, I take the home space, and then it has a natural R by module structure, where R is the T equivariant cohomology of a point. In other words, this is a rank T polynomial ring. Polynomial ring of rank T variables. So these are the main properties of the Hecke categories. As you could imagine, I could generalize it to monodromic version. In functions case, it's chi1 and chi2. Now, they are the characters of TFQ. So, well, function becomes sheaves, so I consider character sheaves on T. So, yeah, if you haven't met with these character sheaves on T, it's just a local system on T, but with a multiplicative structure. So basically, it's satisfied where M is the multiplication map from T cross T to T. So it's just an analog of characters. And the same abstract nonsense, those perverse sheaves categories still holds. You could still define these derived categories with monodromy. And again, you could, for any two sheaves, you could define their convolution products. And the home space between if F1, F2 are in this DL1, L2, yeah, it is still a R by module. Well, you may wonder why we actually study category instead of algebra. What extra information does the Hecke category have? It turns out it has more information. If you take the center of the category, what you get will be the unipotent character sheaves. This is a result by a list of mathematicians, Lustig, Brzokannikov, Finkelberg, Ostrich, Ben-Zvi, Nadler. Yeah, they prove similar versions of this statement. So the punchline is the center can see every representations. Meanwhile, the Hecke algebra, you could only see the principal series. So there are more representations in general than principal series if you're not in type A. For instance, E8 has 13 more has 13 hospital representation, unipotent representation. So yeah, the category has more information. Any questions? Okay. Let me switch the gear and talk about endoscopic group. By a theorem, I don't know who proved it, but yeah, you will see it in Babaki's book. So there is a classification of split connected reductive group. So they are corresponding to a 4 tuples, namely the root datum. So basically the first 2 entries is a 3 abelian group, dual to each other, and then the third one and fourth one are some subsets of these abelian groups which satisfy some reflection properties. And yeah, the association is constructed as follows. If you have a G, then you just take the co-character letters. The character letters co-character letters, root and co-root. So for example, if G is SL2, the torus is one dimension. No, so the character letters and co-character letters are all Z. And then the root and co-root are ±2 and ±1. For PGL2, it's still Z and Z, but this time it's ±1 and ±2. So they're different. So in other words, yeah, these four tuples could detect SL2 and the difference of SL2 and PGL2, despite they have the same Lie algebra. And Langlands has the insight of taking Langlands dual of reductive group. Namely, if you swap these two data, if you swap the character letters and co-character letters, root and co-root, and then they are still represent a split connected reductive group. And this is the so-called the Langlands dual group. So in other words, for example, they are dual to each other, SL2 and PGL2. So you just swap two tuples. Yeah. And then you could get another reductive group. For GLN case, the dual is still GLN. So it's hard to see why, yeah, you want the dual group in GLN case. But in general, the correct notion should consider the dual of Langlands group. Okay, I want to talk about the definition of endoscopic group. But first of all, the endoscopic group depends on the character sheaves L. Here, L. Maybe I use another color. So I want to choose a subset of co-root and call them good, which depends on the choice of L. So as I said before, L could be regarded as a rank 1 local system on T. So it just sheaves on T. And then a co-root alpha check represents a homomorphism from GM to T. So I could pull back along this co-root and get this local system on GM. If this is trivial, then I call it good. Otherwise, I call it bad. So I have a subset of good co-roots for each L. And you could check that these subsets of co-roots are actually additively closed. Namely, if alpha and beta are inside the co-root, a good co-root, alpha plus beta is also good co-root. So now I could define what endoscopic group. If I have an L, then I only need to construct a 4 tuples. The first two are still the same, the character letters and co-character letters of G. But now I just choose the good co-root. And we know that co-root and root are in bijection. So I call a root to be good if its corresponding co-root is good. You can check that they all satisfy the reflection axioms of root datum. So we will obtain back an endoscopic group. So it is split reductive group over FQ. And since I choose the same torus, same character and co-character letters, it has the same maximal torus with G. And since good coroot is a subset of coroot of G, so it's smaller dimension. But let me make a very important remark. This endoscopic group is not a subgroup of G. Let me illustrate it with an example. Suppose my G is symplectic group SP2N, and I choose the unique order 2 local system. So RE is just like the Mobius twist on the torus. And then you could check that, okay, the good coroot are actually, or maybe I say in this way. So first I draw the root diagram and coroot diagram, and then they're dual to each other. So it's just like long root with corresponding short coroot. Yeah, I just take an inverse. You just scale the root to be coroot. And then the good coroot are the diagonal one of this large square. So the corresponding root will be the red circled root. It is a vertex of a square, but it is the smaller square. And we know that this is not additively closed, because these two plus add together, I will get something outside the circle. So yeah, and that's why HL is not a subgroup of G. Because yeah, to check whether it's subgroup, whether it is a subgroup or not, you just care about the root instead of coroot. And in this case, you could check that the endoscopic group with this particular L is the special orthogonal group 2n. And in fact, there are no interesting map from SO2n to SP2n. At least, yeah, from my point of view. And this makes everything related to endoscopic groups so difficult. Because yeah, it's not a subgroup. So it's hard to do the usual function sheaf dictionary thing, because you don't even have an embedding. Are there any questions?
Yes. Could you remind me again, what is the Langlands dual of SP2N? Is it SO2N plus 1? What is the Langlands dual of SP2N?
SP2N.
Isn't that SO2N plus 1?
Yes.
So this is type C. The thinking diagram is look like this. So if you take dual, then it will become type B.
Okay. So, but you do have an embedding of this endoscopic group into the Langlands dual of SP2N, yes?
So
I don't know if that's helpful, but I mean, you do have it, right?
So it's more like there's the Langlands dual of endoscopic group embeds to dual.
Okay.
Because the dual is like the taking dual means the root will become co-root and co-root become root. So by definition, it's additively closed on the right hand side. So it's a subgroup.
Okay, thank you.
Yeah. Yeah, to see which dual group is it, you just like this is simply connected, and yeah, the adjoint group, the dual group will be adjoint. Yeah, the adjoint group for type B. So in this case, SO, yeah. So I could now talk about my main statement. Suppose I have a L, a character sheaves on T. I could consider the endoscopic group HL, and then I could take the loop group of HL. I prove that there's a natural monoidal equivalence of triangulated categories of a of the neutral block. Sorry, the neutral block of the Hecke category and the monodromic Hecke category, Affine, yeah, which preserve these three families. So sending IC sheaf to IC sheaf. In particular, this is T exact. So I didn't prove the whole categories, they are equivalent to each other, but I proved the neutral block of the categories are equivalent. Let me explain what neutral block means. Basically, both categories, the Affine Hecke category and the monodromic Affine Hecke category, can sometimes be decomposed into smaller subcategories. For example, if I consider the Affine Hecke category with no monodromy of H, well, this double coset, this is an in variety. It's just like affine Grassmannian, affine flag variety, if you only consider the right action. This is not necessarily connector because the component is related to the center of H. So if H is not simply connected, then yeah, there are many components. It could be, yeah, the pi zero is not necessarily one. So in other words, yeah, for neutral block, what I mean is I just consider the sheaves support on the neutral component, namely the component containing identity element. So it's just like, yeah, there are many disconnected things of this stack or this variety. I just consider the one containing E. The second example is more interesting. So suppose my G is SP4. Again, my L is order 2, just as above. So H is SO4. The sheaf can actually be supported everywhere because WL is L, just like the, yeah, it's just like a function case, yeah. So for all WL is L. So this affine monodromic Hecke category, the sheaves could support everywhere, but I could actually separate the, maybe I say in this way. So here, this diagram is like, for each dot, it represents an element in the affine wild group. So in particular, there is a finite part and non-finite part. And my claim is for sheaves supporting the red collection and the sheaves supporting the yellow collections, they do not talk with each other. Namely, they don't have X. So basically, I could decompose this DLL into yellow and red as a category. because they don't have X, they don't talk with each other, the objects. And yeah, this phenomenon, is quite surprising to me. And my claim is the neutral block here are the one containing E, the identity double coset. So in other words, the yellow block is the neutral block. So yeah, my main statement is, okay, first, the neutral block is still a monoidal category. Monoidal. Second, this yellow block is isomorphic to the LSO4, the neutral component of LSO4, because SO4 is the endoscopic group. And then the LSO4, the affine flag variety is disconnected. It has two pieces, and the sheaves supported on the neutral component is still a monoidal category, and they're the same. I mean, isomorphic. And this is my main statement as a special case where G is SP4 and L is order 2. So I didn't claim that, the red block, I didn't claim anything about the red block, but only the yellow block in my main statement. Any questions? Yeah, maybe I will give a remark. So basically the neutral block contains almost all geometric information, because the rest, the red block could be obtained from the yellow block by tensoring and other IC sheaves. And when G is adjoined, the set of blocks actually match on both sides. So it's a natural question to ask whether I could extend the equivalence to the neutral block, non-neutral block, and this is a work in progress. I don't think I have time to talk about the proof, but maybe I will stop here. Maybe I will show the main statement again. Basically, I proved something about neutral block. It's a yellow block, not a red block. And then I could match the three families of parallel sheaves together. And because W index, W is it is some element in the alpha bar group. And I think I will stop here.
Thank you. Is there any questions or comment?
Could you explain whether there's any I mean, do you expect the theorem to be true essentially more or less as written as you go beyond the neutral block, or do you think have you already discovered that there's some subtleties that
I think to extend this neutral block to non-neutral block equivalence, I have to compute certain three co-cycles. So because even I match the simple objects, the associativity constraints actually depends on a three co-cycle, which is some kind of combinatorial and algebra computation. So I don't know whether this three co-cycle is trivial or not, but if it is trivial, then the equivalence could be extended. If not, then they are not equivalent.
I see.
Is the non-neutral blocks are the non-neutral blocks module categories of the neutral blocks?
Actually, no, because if you take this as example, yeah, S squared is E, so it's just like group multiplication. The yellow block is a group, but yeah, the red block is not a group. So yeah, if you tensor.
No. I'm asking if this is a module category over the neutral block. So if you tensor the neutral block and the non-neutral block, yeah, you will get itself, right?
Yes.
So do you think it's possible that these two things as module categories are equivalent? Does it make more sense? So instead of being equivalent as monodal categories, I'm asking, so you have shown that they have the same neutral blocks. Then can you say that the two module categories over the same neutral blocks are equivalent as module categories?
I think this is a special case if I could prove that the non-neutral block equivalence, right?
Yeah. If you have that equivalence, maybe you will get
I would
get this as consequence. This is weaker, so maybe
yeah, isn't it nice?
Probably this is true.
I hope it is true. Yeah.
Is it an ignorant question to ask what happens if you replace an Iwahori by a parahoric?
Actually, I have another work in progress, joint work with my advisor Jiwei Yun and also Gerbia, Tilton, and Siwen Zhu about something parahoric version. Yes. Yeah. Try to define. Yeah. Try to match up two derived categories, I guess. Yeah.
Are the K-theories of these categories computable at all?
Oh, it's just the Affine Hecke algebra.
Oh, I see. So that is how you think of categorification. In other words,
yes.
I see. It's actually the Grothendieck group that gives it back to you, I guess.
Yes.
Okay, I didn't catch that point. Thank you.